Hello everyone. The title of this video is Finding the Domain of a Logarithmic Function. Alright, so in this video I'm going to be going over some examples that are taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 6.4, called Graphs of Logarithmic Functions, and I'm under the heading Finding the Domain of a Logarithmic Function. Each example I'm going to do is either going to be one of the examples from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Okay, so now before I go into an actual example, first I want to talk about the graphs of basic logarithmic functions, which I have a page written out here for you. So these are the most basic, or the parent, logarithmic functions. Right, and then every other logarithmic function we're going to see the graph of will be just some transformation of a function that looks like this. So the most basic logarithmic function you'll come across is y equals, or f of x equals, the logarithm base b of x. Right, just basic old x inside the logarithm. And we had some conditions on the base of a logarithm. Right, the base b had to be positive, and we didn't want it to be 1, right, because that would make it uninteresting. And another thing we're going to notice, and we'll see this later when I go to the Desmos calculator, is that the input, right, the number inside the logarithm, also must be positive. So I've got over here x has to be greater than 0. Right. And then we break this up into two cases, just like with exponential functions. And you'll notice that exponential functions and logarithmic functions are inverses. Right, and you'll see the domain and range just switch up. So I've got the same two cases as we had with exponential functions. One case, if the base is bigger than 1, you have a function that looks like this. The point 1, 0, b1, 1 over b, negative 1, and so on are on the graph. And it's an increasing function. Goes up as you go to the right, just very slowly. And it has a vertical asymptote at the y-axis, the line x equals 0. The graph will approach, the y-axis from the right, go down forever, but never actually touch the y-axis. Right, and the reason being is you can only plug in positive numbers. Right, the number inside the parentheses of in the input of a logarithmic function can only be positive. Right, and so the domain is only positive numbers, right, everything from 0 to infinity, not including 0. The range for these logarithmic functions is all real numbers, right, everything from negative infinity to infinity. So it goes down forever and then up forever, right? No gaps. And as I said earlier, right, logarithmic functions and exponential functions are inverses. So the domains and range will switch, right? Hopefully you recall, for an exponential function, b to the x, this was switched, right? The domain was all real numbers and the range was positive numbers. And then instead of having a horizontal asymptote like the exponential functions had, we have a vertical asymptote, right? And that vertical asymptote is for this, these pictures here, x equals 0, the y-axis. Right? The graph approaches the y-axis as you move toward it from the right side, but never actually touches it. And it's an increasing function. Right? As the input goes to, as you go to the right, as the input increases, the output increases, right? And in the other case, if the base is between 0 and 1, right, like a half or 2/3 or something, then you have a function that looks like this. And this is a decreasing function. As you increase the input, the output will decrease, go down forever. Same stuff though, domain's all positive numbers. The range is all real numbers, right? It goes up forever, down forever, and the y-axis is still a vertical asymptote. But this time the graph approaches, goes up forever to the right. The output approaches infinity to the right as opposed to negative infinity in when the base is bigger than 1. All right. And I'd also like to show you some, just some pictures of this. These are hand drawings. So let me show you a better picture of these things on that Desmos calculator, right? Desmos.com, free online graphing calculator. And I'm just going to put in, f of x equals the logarithm base b of x, and we'll add a slider for b, and just make sure, only positive numbers, right? So I'll go from 0 to, say 0 to 10, and have the steps. I'll have the steps be 0.01, really tiny steps. All right. And again, notice when b is 1, nothing's showing up here. But now, because technically it's like when b is 1, you plug in a value, and they're like 1 to what power is 2, nothing. The only value that hasn't, the only input that has any value would be 1, right? And then the output could be anything. So it's like we don't get a really well-defined function when b is 1. But again, you see when the base is bigger than 1, how the graph is, increasing. And I'll put in the y-axis as well, maybe highlight it and dash it. You can see that that's a vertical asymptote. Right, the graph is approaching. Now I know it looks like it touches it down here, but if you zoom in close enough, you can see that the graph doesn't actually touch the y-axis. It just approaches it from the right. But yeah, when the base, here the base is 1.76. When the base is bigger than 1, you have an increasing function. Right. And some key points on these graphs. The point 1, 0 is going to be on all of them. Right, all the basic ones, that purple point that just showed up. But so will the point, b comma 1. Right. So again, you plug in whatever the value. If it's base b, and you plug in whatever the value of b is, the output is 1, since b to the 1 is b. Right? And then another key point would be 1 over b, and if you plug that in, the output is always going to be negative 1. Right? B to the negative first is 1 over b. And I'll change the colors of these so that they're all the same. Let's make them all purple. Okay, and you can see here, so no matter what the base is, these 3 points, no matter what I change b to, these 3 points are on the graph of the function. All right, so that's when the base is bigger than 1, and then you see when the base is less than 1, so I move b to like 0.9 or something. See how now it's a decreasing function, right? Like in my hand drawing. Right. But again, those same points are on there. Here's, b is 0.4 right now. There's b comma 1, and then 1 comma 0 is on all these basic logarithmic functions, and then 1 over b would be 2.5, and then negative 1, right? But the 3 points I put here are the ones that are labeled, and they're always on this basic logarithmic graph. Okay. Alright, so now that we have at least the basic graphs down, we should be able to now go into the examples for this video. Alright, so for all the examples, I have the following instructions. I'm asked to state the domain, the range, and the vertical asymptote of the given function, the given logarithmic function. Alright, so here we have f of x equals the log base 5 of x minus 2, and then afterwards plus 1. Right, so this is the log base 5 of x, but just, transformed. Right? X is replaced by x minus 2, which would shift it to the right 2 units. And then you have this plus 1 after, which would shift it up 1 unit. I'm hoping you remember all the transformations, function transformations from chapter 3 of this text from OpenStax. But I'm not going to write all that. All right? What we're asked to find first is the domain. And finding the domain of a logarithmic function is pretty simple in my opinion. Because remember what I mentioned earlier, the expression inside the logarithm, the number inside, has to be positive. This must be positive. Okay, and then I set up an inequality that states this. So x minus 2 must be greater than 0. And then I solve this for x, to determine what values of x I can actually plug in. We'll just be adding 2 to both sides. X must be greater than 2. Right, there's a description of all the numbers you can plug in. Only numbers greater than 2, right? So the domain of this function is all the numbers greater than 2, right? So everything from 2 to infinity, but not including 2. You can't plug 2 in because that would give you the log of 0, and that's not defined, as we'll see. Again, I'll show you a table when we go to graph this in Desmos, and if you plug in a value of x that makes this negative, the log of a negative or the log of 0, you're not going to get a real number output. They'll just say it's undefined. The number inside has to be positive. Now the range. The range for any logarithmic function is going to be all real numbers, right? So I'm not even worried about any calculations to do here. This is an easy thing. This should be the case for all the examples I look at here. And then the vertical asymptote. Once you've stated the domain, this vertical asymptote should be easy to identify. We can only plug in values greater than 2. So x equals 2 is going to be the vertical asymptote. The graph will not have any points on this line and will get really, really close to this line without actually touching it. You could have also figured this out by doing transformations, right? The original log base 5 of x, the y-axis is the vertical asymptote, but then I replace x with x minus 2, and that would shift it to the right 2 units. And shifting to the right 2 units would also shift the asymptote. The asymptote would move from the y-axis to x equals 2. And this is all we're asked to do. Now I'm also going to make a graph and show you a graph for a bunch of these. So now if you have graph paper, that would be better, but I do not, unfortunately. So here's x equals 2. Throw in a little dashed line here. Let you know that that's an asymptote. That doesn't actually belong to the graph. And then I'm going to plug in some numbers so that the number inside the logarithm is a power of 5. In fact, let me just make a table here for you. So x, f of x. And again, I want to plug in numbers. So I want to plug in values of x so that after I subtract 2, I get a power of 5 in here. Right here are the powers of 5. or not all the powers of 5, but I'm talking about like, dot dot dot, 1/25, that's 5 to the negative second, 1/5 is 5 to the negative first, 1 is 5 to the 0, 5 is 5 to the first, 25 is 5 to the second, and so on. So for instance, it's easy to get 1 in here. If I replace x with 3, right, I'd have the log base 5 of 1, which is 0, plus 1 is 1. So 3, 1 would be a point on the graph of this function. There we go. And so that takes care of the 1 there. And then what if I wanted 5 in here? I'd have to replace x with 7. Right? 7 minus 2 is 5. Then the log base 5 of 5 is 1. Right? 5 to the 1 is 5. And then 1 plus 1 is 2. Right? So 4, 5, 6, 7. Input 7, output 2. And you can see it's going to be a increasing function, right? Very slowly increasing, right? To get an output of 3, I'd have to go out to I'd have to plug in 27, right, to get an output of 3. So if I plug in 27, right, 27 minus 2 is 25, and the log base 5 of 25 is 2, plus 1 is 3. So I'm not writing that one in, right? But that's way off the screen, off my paper. But how about between 2 and 3 here? There should be some points, And this is just going backwards. What if I want 1/5? Right? So I plug in 2 and a fifth, or 2.2. 2 and 1/5. Plug in 2.2 for x. You get the log base 5 of 1/5, which is negative 1, plus 1 is 0. So here's a 2.2, or 2 and 1/5, and then the 0. And the closer to 2 you get, if I plugged in 2 and 1/25, I'd get, negative 1. And then 2 and 1/125, I'd get negative 2, right? The closer to 2 I plug values in for, the bigger negative the output will be. Right? And then the graph is like my little picture earlier of logarithms. The x equals 2 is an asymptote, right? The graph is approaching x equals 2, going to a negative infinity on the right side here, but not actually touching it. And then it's an increasing function, right? It's just very slowly increasing. And there's a rough hand sketch of this graph. But now I could also, let's go to the Desmo site and look at a nicer picture of that and see that all my points are correct on there. And all right, so back here, let me just clear all this stuff out. And the function we were given, f of x equals the log base 5 of x minus 2 plus 1. You see this blue graph here. Now, hopefully it's obvious that x equals 2 is the vertical asymptote. And I'll make this a dashed line. And then once again, I know it looks like the graph hits the asymptote, but if you zoom in close enough, it doesn't. All right, you zoom in close enough, you'll see that the blue graph indeed does not touch that dashed line, does not touch the asymptote. All right, and then if I were to make a table for this function, now you see that the default table has inputs of negative 2 to 2. See how all those are giving me outputs that are undefined? That's because these values aren't even in the domain. Remember, we said the domain is only values greater than 2. Right? And if I plug in 2, I get 0 inside the log. That's not good. If I plug in 1, I'd get negative 1 inside the log. That's not good. You can't have numbers that are not positive inside the logarithm. Right? But I could plug in, like I did earlier, 2.2. See how the output's 0? Just like in my drawing earlier. Plug in 3 for an output of 1, like in my drawing earlier. Plug in 7 for an output of 2. If I plugged in 27, right, got an output of 3. I'd have to go all the way out to 127 to get an output of 4, right? Because that would give me 125, which is 5 to the third in here. So you have log base 5 of 125 is 3 plus 1 is 4, and so on, right? And then, like I mentioned, I'd have to plug in, 2 and 1/25. That'd be 51/25 to get an output of -1. And whatever, right? But again, the closer to 2 I get from the right side, the bigger negative the output will be. Okay, great. All right, next example. I'm doing pretty much the same thing for all these problems. I might not look at the graphs all the time, but we're asked for the domain, the range, and the asymptote. All right, so just like example 1, here this function is f of x equals the log. Now remember, when there's no base, this is the common logarithm. All right, remember this is base 10 when there's no base. You can write a 10 in there. There's nothing wrong with that. Of 5 minus 2x. And as I did in example 1, the expression 5 minus 2x must be positive in order to get real number outputs. All right, so I'm going to set up a little inequality involving this 5 minus 2x. So 5 minus 2x must be greater than 0. Then we solve this, right? So negative 2x must be greater than negative 5, and then dividing both sides by negative 2 would flip the symbol, and then negative 5 divided by negative 2 is positive 5 halves, 2.5. So my domain, the values I'm allowed to plug in are only values less than 2.5, less than 5 halves. So those would be the values from negative infinity up to 5 halves, right, but not including 5 halves. And then as I mentioned in problem 1, the range for all these logarithmic functions is all real numbers. You'll get every possible output. And then the asymptote, right, the asymptote is going to be x equals 5 halves. Because I can only plug in numbers to the left of 5 halves. So x equals 5 halves, x equals 2.5, that's where the asymptote's going to be. And again, that's all they want. All right, now I'm going to do my best to make a rough sketch of this over here. All right, so here's 1, 2, 3, and then 5 halves, right, is here, but 2.5. So there's a vertical asymptote here. And then the entire graph is going to be to the left of this, right? The domain is all values less than 5 halves. Now, this logarithm, right, this logarithm has a base of 10. So what I want inside here are powers of 10. Right, what I want to have inside the logarithm are powers of 10 to make these nice and easy. Now that would be like, 1/100th. That's 10 to the negative second. 1/10th, that's 10 to the negative first. 1, that's 10 to the 0. 10, 100, 1,000, and so on. All right, now to get 1 in there, we can just set this equal to each of these values. 5 minus 2x would equal 1 when x equals 2. All right, so when x is 2, you get 0. Right, 5 minus 4 is 1. Log base 10 of 1 is 0. So 2, 0 is on this graph. 2, 0 is the x-intercept. All right. Then to get 10, I'd have to plug in negative 2.5. So negative 2, negative 3, here's negative 5 halves. Right, if I plug in negative 5 halves, this would become positive 5. 5 plus 5 is 10, and that would give me an output of 1. Right, the log base 10 of 10 is 1, so negative 5 halves 1. And then hopefully just from these 2 points alone, and it's just like exponential functions, you only really need 2 points to be able to determine how the graph's going to look. you should see that this is a decreasing logarithmic function here. Maybe doing something like this, and then again approaching this asymptote, not going beyond the asymptote. Something like that. That's a very, very rough hand drawing. And let's take a look at that in Desmos, right, and see if my hand drawing looks even remotely similar. So the function we're given here is f of x equals the log, and this is base 10. Just write log 5 minus 2x. Yeah, that looks pretty similar to what I had. X equals 5 halves, as I mentioned, is the asymptote. Make that a dashed line. You can see that the graph approaches that line but doesn't actually touch it. Again, I know it looks like it touches, but if you zoom in close enough, you'll see that the red graph doesn't touch the blue dotted line. I mean, I'm zooming in real close here, but eventually you'll see it, that they don't actually touch. Alright, and then just make a table here, and now all these values are in the domain, right? All these default values, because we're plugging in values less than 2.5, and all these values are less. But you see 2, 0, that was one of my values. Negative 2.5, I said would give me an output of 1, right? And you can plug in other points that you wish, right? And then they plot them here on the graph for you. You can see them. So here's negative 2.5 comma 1. Here's 2, 0, and then other points, of course. Yeah, great. So it looks like my drawing was reasonable. Okay. All right, the next example is very similar. Another log base 10 of x minus 5, and then you have the plus 2 after, which would do a vertical shift by 2 if you were keeping track of transformations. But once again, I'll start off with the domain. What am I allowed to plug in for x? All right, so this x minus 5, remember, this expression, this number inside the logarithm has to be positive, has to be greater than 0. And then solving for x, x has to be greater than 5. So the domain of this function is every number from 5 to infinity, right, but not including 5. Right, just greater than 5 only. And as I've been stating, right, the range for all of these logarithmic functions is all real numbers. And then the vertical asymptote, once again, if you know the domain, it should be simple to determine this. I can only plug in numbers greater than 5, so x equals 5 will be the vertical asymptote. And that's all they wanted, right? But I still will make a rough sketch over here. So 1, 2, 3, 4, 5. Right, there's x equals 5. There's going to be a vertical asymptote there. And then I'm going to plug in some numbers, so that we get powers of 10, which I have listed up here already. Now obviously if I plug in 6, you get 1. The log of 1 is 0, but then you got the plus 2. So 6 should have an output of 2. Right, the ordered pair 6, 2 will be on this. And then if I plugged in 15, 7, 8, 9, 10, 11, 12, 13, 14, 15. If I plug in 15, that gives me 10 in here. The log of 10 is 1, plus 2 is 3. All right, so 15, 3 would be on the graph as well. And that should be enough to make a rough sketch. Now you can also plug in some number between 5 and 6. Like if I put in 5.1, then I'd have 0.1 in here, 1/10. This would be negative 1 plus 2 is positive 1. All right, if I plug in 5.1, the output will be positive 1. Right, and if I plug in 5.01, the output would be 0, and so on. Like the closer to 5 I get, the lower the output. And I'll do something like this, and again approach the the asymptote but not actually touch it. And then over here it's going up forever. It doesn't look like it from my drawing, but it's going up forever, just very slowly. All right, and once again, you can punch this into the Desmos calculator. Let's take a look just to make sure my hand drawing is reasonable. All right, and then after this example, I'm just going to find the domain, range, and asymptote and leave the graphing to you. All right, so f of x equals the log base 10 of x minus 5, and then plus 2 moves that graph up 2. And yeah, I hope you can see x equals 5. This line here would be the asymptote. There's 5.01 comma 0, right? I said that would be the x-intercept earlier, and then it's got all the points I need on here. 6 comma 2 is on here. Right, there's 6 2. That was on my graph. You should have 5.1 comma 1. It's there somewhere. There it was. There it was. I had it for a second, but 5.1 comma 1 is on there. And it looks like my hand drawing. Not terrible, not terrible. Great. Alright, so for the rest of the problems, I'm just going to do the domain, range, and asymptote. And I might make a rough hand sketch. I'll leave the graphing mostly to you, though, from here on out. Alright, so f of x equals, the log base 3 of x plus 4. So remember, for the domain, right, that expression inside the logarithm has to be positive. Right, so x plus 4 must be greater than 0. So that means x must be greater than negative 4. So the domain of this function is all numbers, from negative 4 to infinity, but not including negative 4, right? All the numbers greater than negative 4. And once again, the range is all real numbers. Easy enough. And the asymptote, I'm just going to put ASYM. The asymptote is x equals negative 4. I can only plug in numbers greater than negative 4, so the asymptote is going to be at negative 4. Again, a very rough sketch here, real quick. I think this might be the last one I do. Negative 1, 2, 3, 4. There's where the asymptote's going to be. And then if I plugged in, negative 3, you have an output of 0, because that'd be the log of 1. And I'm looking to have powers of 3 in here, right? And since the base is 3, so 1, 3, 9, or 1/3, 1/9, right? Negative 3 plus 4 is 1. And then negative 1 plus 4 is 3, and the log base 3 of 3 is 1, so you have negative 1, 1. And then the graph should be looking like this, right? It's increasing, but approaching the asymptote like this from the right side, and then increasing as you go from left to right. Something like that. Okay. Alright, next. Here we have g of x equals the log base 5 of 2x plus 9, and then minus 2. Right, so this 2x plus 9 expression must represent a positive number. Right, so 2x plus 9 must be greater than 0, meaning that x must be greater than 9 halves. Right, negative 9 halves, sorry. Subtract 9, divide by 2. X must be greater than negative 9 halves, or negative 4.5. So the domain of this function is everything from negative 9 halves to infinity. Again, not including negative 9 halves, all the numbers greater than negative 9 halves. The range is all real numbers. And the asymptote, the vertical asymptote, is x equals negative 9 halves. Right, because you're plugging in all the values greater than negative 9 halves. So there's going to be an asymptote. I know I said the last one would be the last one, but why not just throw in a quick sketch of most of these? Alright, so negative 1, 2, 3, 4, 5, negative 5, negative 4. Here's negative 9 halves. Right, an asymptote there. And the base on this is a base of 5, right? So I'm looking to have powers of 5 inside this. 1, 5, 25, or 1/5, 1/25, whatever. You know, if x were negative 2, I can see right away you'd have 5 in here. The log base 5 of 5 is 1 minus 2. Then you have the minus 2 after. 1 minus 2 is negative 1. So you have negative 2, negative 1. If I want this to be equal to 1, just plug in negative 4, right? 2 times negative 4 is negative 8, plus 9 is 1. The log base 5 of 1 is 0, minus 2 is negative 2. Right? So negative 4, negative 2 would also be on the graph, and then hopefully from just those 2 points, you can figure out it's an increasing function and looking something like this. Right, now it eventually hits the x-axis. It goes up forever, just very slowly. The only asymptote here is at x equals negative 9 halves. Okay. Alright, next. I'm doing the same thing for all these. Domain, range, asymptote. So here f of x equals the log base 2 of 12 minus 3x, and then afterwards, you know, minus 3. So once again, finding the domain is simple enough. The expression inside the logarithm must be positive. Right, so 12 minus 3x must be greater than 0, meaning that, you know, negative 3x must be greater than negative 12, and then dividing by negative 3 will flip the symbol, and then negative 12 divided by negative 3 would be positive 4, so x must be less than 4. Alright, so the domain of this function is all the numbers from negative infinity up to 4, right, but not including 4, all the numbers less than 4. Range is all real numbers. And the asymptote will be at x equals 4. And that's all they wanted. Alright, but I think I can make another rough sketch pretty quickly. So 1, 2, 3, 4. Right, there's where my asymptote's going to be. And the graph is going to be all to the left of that, right? The domain is values less than 4. Alright, so I'm trying to, now the base on this log is 2. So I'm looking to make powers of 2 in here. 1, 2, 4, 8, you know, 1/2, 1/4, 1/8, and so on. If I plug in 11 thirds, I'll get 12 minus 11, I'll get 1 in here. Now 11 thirds, that's 3 2/3. Here's 11 thirds, 3 2/3, right? That's where this will be 0, and then minus 3 is negative 3. So you have 11 thirds, negative 3 for that point. And then if I want 2 here, you know, this needs to be equal to 10. 10 thirds would work. 10 thirds is 3 1/3. And then I get the log base 2 of 2. And that's 1 minus 3 is negative 2. Right, so 10 thirds, negative 2, 11 thirds, negative 3, and you see the decreasing nature of this function. It's going to be doing something like this. Alright, but something like this. And it's going to hit the x-axis eventually, right? It's going up to the left forever. Again, you can play around with that. You know, make a graph in Desmos, whatever you want. Okay. Now here, g of x equals, now remember the natural log, remember this is the log base e. That's what that ln represents, and e was about 2.7, right? 2.718 and so on, of 3 minus x. So once again, you know, for the domain, the number inside the logarithm, the expression inside, 3 minus x, must be positive, must be greater than 0. And I would just simply add x and switch sides. X must be less than 3 here. Right, 3 would be greater than x, meaning x is less than 3 if you switch sides. Right, so the domain of this function is everything less than 3. So from negative infinity up to 3, but not including 3. Range is all real numbers. That's the case for all these logarithmic functions. And the vertical asymptote is at x equals 3. Right, we use everything less than 3 in the domain. All right, so that's what they wanted. Very quick. And a quick sketch. So 1, 2, 3. There's an asymptote there, and then the rest of the graph is going to be to the left of this. Now base E, obviously if I plug in 2, I'll get natural log of 1, which is 0. So 2, 0 is on the graph. And then if I plug in 3 minus E, I'll get the natural log of E, which is 1. Now 3 minus E would be about 0.3. Right? Say there's 3 minus E, about 0.3, and then that'll give me an output of 1. Right? So 3 minus E, comma 1, and there's a couple points, and you should only need a couple points in the asymptote to be able to draw a rough sketch of this logarithmic function, that decreasing function there. And again, you can go to Desmos and check it out and see that this drawing is similar. Wonderful. All right, so I got one more page with this kind of stuff on it. So here, f of x equals 3. Now don't forget that, after we take the logarithm, we're then going to multiply by 3 and then add 2 to get the output. So 3 times the log of negative x, remember this is base 10, common log, plus 2. So again, this expression inside, this negative x, must be greater than 0. Dividing both sides by negative 1 will flip the symbol. So x must be less than 0. Right, so the domain of this function is all values less than 0. Right, from negative infinity to 0, not including 0. Range is all real numbers. And the asymptote will be x equals 0, right, the y-axis. And that's all they wanted, but again, I'll make a quick sketch. All right, so 0, the y-axis is the asymptote, right, x equals 0. There's the asymptote. And I can only plug in values less than 0. Now obviously if I plugged in negative 1, that'll give me 1 in here, which has a logarithm of 0, and then 3 times 0 is 0, plus 2 is 2. So negative 1, 2 is on the graph. And then if I plugged in negative 10, negative 10, 2, 3, 4, 5, 6, 7, 8, 9, 10. Plug in negative 10, you get the log of 10, which is 1, times 3 plus 2 would be 5. Right, so negative 10, 5 would be on the graph. And again, once you have 2 points and the asymptote, you should be able to make a rough sketch of any logarithmic function, right? So it's looking something like that. Okay, and then the final example I have for this video where I'm doing the same exact stuff. F of x equals the log base 3 now, right, base 3, of 15 minus 5x plus 6. Right, so once again, the domain, very easy to determine, I feel. Take the expression inside the logarithm. This number must be positive. So 15 minus 5x must be greater than 0. And if you subtract 15 and then divide by negative 5, right, that'll flip the symbol. And negative 15 divided by negative 5 is positive 3. So x is going to be less than 3. All right. So the domain of this function is all the numbers less than 3, so everything from negative infinity up to 3, not including 3. The range is all real numbers again. and the asymptote is going to be at x equals 3. And that's all they wanted, and once again I'll make a quick sketch. So 1, 2, 3 on the x-axis, vertical asymptote there. Alright, now I'm looking for powers of 3 inside the logarithm. Now to make this equal to 1, x would have to be 14/5, which is 2.8. Yeah, so 2.8. That gives me the log base 3 of 1. And that's 0, and then plus 6 would be 6. So you got 2.8 comma 6. And then if I want 3 in here, I'd have to plug in 12/5, which is 2.4. So 2.4 would give me the log base 3 of 3, and that's 1 plus 6 is 7. So I have 2.4 comma 7, 2.8 comma 6. You can clearly see now, hopefully, the direction of the, once you have 2 points in the asymptote, and you can draw a rough sketch. And it should look something like that. Wonderful. But hopefully after watching these, you can tell how to easily, given a logarithmic function, should be able to state the domain, range, and asymptotes for that function pretty easily. And that's it. Alright, so I'm hoping that watching me go through these 9 examples here help you in some way when you're asked to find the domain of a logarithmic function on your own. Alright, thank you very much for watching.